On this slide, we're exploring what happens when our model is too simple, far too complex, or just right. On the left, you see the underfitting scenario. Here, our decision boundary is just a straight vertical line. It's far too simplistic to capture the true pattern in our data. Many blue points on the right actually belong to the red class. This model has high bias and low variance, and it simply can't adapt to the underlying structure. On the right is the overfitting case. The boundary twists and turns to perfectly separate every red and blue point in the training data, even the noise. While it achieves nearly zero training error, it has learned spurious patterns that won't hold up when we see new data. This model has very low bias but extremely high variance, and it will likely fail to generalize. Finally, in the center, we have the optimal model. This straight but tilted boundary balances bias and variance just right. It captures the general trend in the data without trying to chase every single point. As a result, it achieves strong performance both on our training set and on new, unseen examples. The takeaway is that we need to find that middle ground, our sweet spot, where the model is flexible enough to learn the true signal, but not so flexible that it memorizes the noise. On this slide, we're looking at how training and validation errors evolve as we crank up model complexity, and why cross-validation is our compass for finding the sweet spot. Starting at the left, in the underfitting region, both the red curve, training error, and the blue curve, validation error, are high. Our model is far too simple to capture the underlying signal. As complexity increases, the red curve slopes steadily downward. Our model fits the training data better and better, but the key story lives in the blue validation curve. Notice that the validation error initially falls alongside the training error, reaches a minimum at the green vertical line, our optimal complexity, and then begins to rise again. That upward turn signals overfitting. The model is now tailoring itself to noise in the training set, boosting training performance at the expense of generalization. By tuning our hyperparameters to minimize this cross-validated error, we lock in a model that balances bias and variance, and that's the one we confidently carry forward to our final test set into real-world data. Support us by liking and subscribing to our channel.